all.
Okay, this is figure 5.9, the geometry of binary temperature composition diagrams. The binary temperature composition diagrams, there are all binary temperature composition diagrams really have only 2 or 3 structural units. You have invariant lines, which are like a eutectic type invariant at the top there, or you have a peritectic type invariant at the bottom. You have 3 phases with 2 two-phase regions going up and 1 two-phase region coming down. Or you have a peritectic type with 2 phase regions, 1 two-phase regions going up and 3 two-phase regions coming down. Okay. Forget the dashed line. The dashed lines were trying to make a different point. If you have something like this, here you have alpha, beta, and gamma. And then the 2 phase regions. That's a eutectic type of invariant. Alpha, beta, gamma could be solid, liquid, or gas. Okay. Upon cooling, that's temperature going down. The eutectic type reaction is beta gives alpha plus gamma. So as you cool the liquid down, and as you cross this infinitely narrow 3-phase region, the beta forms alpha plus gamma upon cooling. Okay. You can have a peritectic type invariant, which is just the other way around. In that case, you have alpha, beta, gamma. You have 1 two-phase region going up and 2 two-phase regions going down. And there, it's upon cooling. Again, it's always upon cooling. By alpha plus gamma gives you beta. That's your peritectic reaction, peritectic type reaction. Okay, so going down, it's always the center. The phase in the center gives you the 2 extremities. Here, the 2 extremities give you the phase in the center. One's just the back. So it depends. If, I mean, now you can have all the invariants you have are like that. If beta is liquid and alpha and gamma are solid, then that's a eutectic. If all 3 are solids, we call it a eutectoid. There's other types of invariant eutectics. That could be a monotectic. If this was liquid 1, liquid 2, and solid, then it's a monotectic. This becomes a miscibility gap then. So liquid 1, liquid 2, and solid is a monotectic. We talked about that one. That's a eutectic type invariant. Eutectoids, you have a catatectic. Catatectic is liquid, solid, solid. These are kind of rare, but they're kind of fun. A catatectic, this is all in the text there. Catatectic could look something like this. Here you have liquid, solid 1, solid 2. So it would be solid, the catatectic reaction is solid 1 gives you liquid plus solid 2. It's a catatectic invariant. Catatectics could be kind of disturbing if you were to, there are phase systems like this. Say you were to cool, you had an alloy at this composition here and you cooled it, all right, at equilibrium. If you were to cool that at equilibrium, your liquid would pass into the 2-phase region. When you reach this point, you'd enter into a complete solid. Oh, I got this backward. Solid. What is catatectic? Yeah, I'm gonna at the wrong. So let's just move it over to here then. Let me draw the, say this would be my, I take an alloy up here and I cool it. Okay, so what happens now is I start up here with liquid, I go through a liquid plus solid 1, then the solid 1 is completely, when I reach this point here, my liquid has completely disappeared, my alloy is totally solidified. Okay, I continue down and now my catatectic reaction occurs, and when I reach this temperature I find the liquid's appeared again. So this could be disturbing. You cool it down. Okay, as you cool it, a liquid forms. Could be disturbing. So those are peritectic type reactions, and then you can have them the same kind of thing with gas phases and solids and gases, and many of these have no names, but it's a or a peritectic type reaction is obviously a real peritectic would be liquid, solid, solid, as we've talked about, or 3 solids is a peritectoid. A syntactic would be liquids on either side, and so here liquids on either side and a solid in the middle. And I have seen syntactics in your potassium zinc system. The system potassium zinc. Potassium zinc, you have a liquid miscibility gap, liquid 1, liquid 2, and here you have a compound, a solid compound. The solid compound is KZN12. So as you heat the solid compound, it dissociates into two liquids. This is an unusual thing, but that is a syntactic, SYN tactic. And there's all sorts of other possibilities. And then you can have maxima and minima in two-phase regions, and that's it. Those are the entire, all the geometrical units you can have. You have extension rules. This is an incorrect extension. Why is that an incorrect extension? This line here must extrapolate into this region. This is correct. This line here extends into the two-phase region. Well, clearly what happened, this is then this line here, thermodynamically. This line, if it were to move horizontally across here, I'm in the gamma phase, and this line represents thermodynamically when the chemical potential of the alpha phase becomes such that it appears. Okay, so this line here is the locus of your thermodynamic equations when the gamma phase just starts to precipitate alpha. So clearly the extension, there's no reason why that thermodynamic line should suddenly change direction at this point. So this extrapolated line also is the line where alpha precipitates from gamma, but you haven't drawn it that way. You've drawn it here as suddenly alpha no longer precipitates from gamma at that point. This is just, right? This is a thermodynamic line, and it must continue on this way. Here you're okay. Here this is the line where gamma precipitates from alpha, and its extension is in fact the metastable extension. If beta did not appear, then this dashed line would be the line at which you would get gamma precipitating, but the beta precipitates before the gamma. So that's okay. So this is reasonable, but this is not possible. Same thing here. This is a correct extent. These are correct extensions. All of the extensions of these phase boundaries must pass into the two-phase region. Like here, they can't go like this. Okay, then you go to any real phase diagram. So let's go back to, way back to number 1, I think. Let's make these smaller. Alright, this is way back to figure 1 at the very beginning, and so there you have the iron molybdenum phase diagram, and all you see that this is always, you have peritectic-like regions. That's a real peritectic. You have eutectic-like regions. This is invariance. This is a eutectoid, and so on. You have various phases. This is a peritectoid. This is a eutectoid down here. So this is a minimum that occurs very close to there. So this is just a mixture of all the different. Okay, but you can see that in any binary phase diagram you only have two types of invariants, and you have possibly minima and maxima. Right. And two-phase regions that the pure component must join together, of course. But that's about it. So the geometry, temperature diagrams, are always based on that. Okay, so now I'm back to, I just want to talk more about phase diagrams in general. Talked about binary temperature composition phase diagrams, but there are all kinds of phase diagrams. And I just went through in the introduction to this chapter, starting on page 3. Starting with this, I introduced a bunch of different kinds of phase diagrams, different way. Phase diagram is simply a geometrical representation of the phase equilibrium. Okay, so the axes in general, then you want a two-dimensional phase diagram. You have two variables as axes, and you keep other variables constant. Now we'll talk a bit later about, you can't just do anything you want. Well, you can, I suppose, but what you'd like is you would like your phase diagram to be single valued. And that is, when you point at a point on the phase diagram, you want there to be only one equilibrium at that particular point. Okay, when I point to this point, I got the mu plus the BCC phase, and that's it. There's no two phase regions crossing each other. You want a single valued phase diagram. Then there are certain rules about what you can plot versus what. Now all of these diagrams seem to follow different geometrical rules. I talked about here just a minute ago the rules that govern binary phase diagrams. There are many other kinds of phase diagrams. They all seem to obey different kinds of rules. I want to show you a bunch of diagrams that are useful, and then we might talk a bit about the actual rules that govern phase diagrams. So that's one kind of phase diagram. Another diagram that's very important is this is a ternary section. So this is a slice through a phase diagram at a constant temperature. In this particular case, it's 25 degrees Celsius and 1 atmosphere. So there's your magnesium, aluminum, zinc system at 25 degrees and 1 atmosphere. So you have single phase regions. Single phase region can occupy an area. Like this black region here is MgZn. MgZn can contain a certain amount of aluminum. So this is a one-phase region. It does have a certain width as well. It's not completely stoichiometric. You have in two-phase regions you have tie lines. So these are two-phase tie lines. So this is the FCC aluminum phase, which is basically a point, and this is a two-phase region where it's in equilibrium with the tau phase. Okay, so every one of these lines, one end of the line is the composition of one phase, the other end of the line is the composition of the other phase. You all know this, right? Two-phase region. And you have three-phase triangles, which I've indicated by the letter 3. Number 3, and the three-phase triangle. Anywhere in that triangle you have three phases whose compositions are given by the corners of the triangle. Okay, the composition, so within that three-phase region, the composition, anywhere in this three-phase region, the tau phase is exactly that composition at that corner, the beta phase is exactly this corner composition, and this phase is exactly this composition. All that changes as you move in that region is the relative amounts of the three phases, but their compositions stay constant. And the two, if you're on a tie line, this is a straight line. On the tie line, anywhere on that straight tie line, you have the phase at one end of the tie line in equilibrium with the phase at the other end of the tie line. Okay, the only thing that changes as he moves along the line is the relative amounts of the phases. It's the same as in a binary system. If we're in a two-phase, so I'll flip this around. If I'm in a two-phase region here, the two phases in equilibrium at constant temperature are the BCC phase at this end of the tie line, the liquid at this end of the tie line, and all that changes as you move between them is the relative amounts. Anyway, you all know this diagram. This diagram looks looks very different from the binary diagram. If we now want to go to, what happened to figure 3? Figure 2. Figure 4. Here's figure 3 after figure 4. Okay. There's figure 3. Okay, how did that happen? Here. Anyway, there's figure 3A and B. Let's just look at figure 3A. Figure 3A is the same system as figure 2. So this is the zinc magnesium aluminum system, but at a constant mole fraction of zinc versus temperature. So you imagine you've got this system here, this phase diagram here. This is a 10% zinc. So this is here you've really got you have a triangular prism. This is the base of the prism, and then you're going up in 3 dimensions. Right? And this is your composition triangle, and then temperature would be a vertical axis. Okay, so this is a horizontal, so if temperature is a vertical axis, it's a horizontal slice at 25 degrees. Horizontal slices at any temperature would look different, but they'd obey the same geometrical rules. You'd still have triangles, two-phase regions, one-phase regions, tie lines. So now I'm going to take, in this prism, I'm going to take a constant mole fraction line of zinc as 10%, and I'm going to make the vertical axis temperature. So I'm taking now a vertical slice through the diagram at a constant mole fraction. And that's called, this is called an isotherm, of course, because it's a constant temperature. A constant composition slice is called an isopleth. Pleth has got to be some Greek word meaning composition, I guess. Okay, so I'm taking an isopleth. Isopleth doesn't have to be at a constant mole fraction. It could be any line across here. It is an isopleth. So the figure 3A is the isopleth at constant mole fraction of zinc is 0.1. And so there we go. So this is it. So this is temperature versus the molar ratio of aluminum to magnesium at a constant mole fraction of zinc of 0.1. So the isopleth across that dashed line. This is the ratio of aluminum to magnesium plus aluminum in any phase. So what I'm really plotted here is this is a better way of doing it. This axis here goes from 0 to 1. It's the aluminum magnesium ratio when the mole fraction of zinc is 0.1. So In other words, you're plotting compositions along this line from 0 at this end over to 1 at this end. Actually, the two diagrams, 2 and 3A, intersect along this line here. This line is 25-degree line along that zinc line. So if you go along this line, you look at the phases, you have this 2-phase region, then you have the 3-phase region, and you cross all these various regions at 25 degrees. So take the sequence of phases, go left to right, going through the sequence of 2, 3, 1-phase regions, and convince yourself that that's exactly the same thing as you go along this line from left to right. Okay, everything is. So this dotted line here and the x-axis of this diagram are the same thing. Okay, now then you have all the various regions here, 1-phase, 2-phase, 3-phase. You see that in some ways this isopleth looks like a binary phase diagram. You have sort of invariant looking things, but then upon closer inspection it doesn't, of course, because here you've got 4 phases, meaning along that line. Here you've got something, 4 lines coming together. Okay, so this diagram does not. What is really important in an isopleth, and it's often misunderstood, is the isopleth. This is the overall composition along that line, but this does not give you the composition of the 2 phases in equilibrium. Because the 2 phases, the individual phases don't have to have compositions on that line. So here, if you're in a binary phase diagram, you know, the general rule, if you're in a binary phase diagram and you have a tie line, well, anywhere on this tie line you have, this phase is in equilibrium with this phase. So you can read not just the overall composition, but the composition of each individual phase. You certainly cannot do this here. Here, for example, you have a liquid phase and you have an FCC phase. But if I draw a tie line between one end and the other, this is not the composition of the liquid phase. The liquid phase composition varies as I move along here. Because simply, you're in along this line, we're in a 2-phase region, but the 2-phase region, the tau phase and the beta phase don't have compositions on that line. This is just your overall composition. It's not the composition of the individual phases. Right? No? If I'm at this point here, okay, point P. Okay? At point P, my overall composition is 10% zinc. But I'm on a 2-phase region. My tau phase has this composition, about 40% zinc, and my beta phase at equilibrium has 2 or 3% zinc. The overall is 10, but the individual phases don't have 10% zinc. I mean, they might if they lay on the line, but they certainly in general don't. In fact, in this case, none of them do. Here you're in the 2-phase region with FCC and tau, and the FCC is almost pure aluminum. The tau has a lot of zinc. The average is still 10%. And as you move across that region, as I move across this 2-phase region from left to right, the composition of the tau phase is changing all the way across. So I certainly, by no stretch of the imagination, in fact it's totally wrong, but you will sometimes do it, if you take tau plus gamma region, I certainly cannot take one end of this phase, say this is the liquid and this is the FCC, because they're not on the line. Okay, so isopleths, I mean, they might be in some cases. And in some cases, you can have all the isopleths, or all the points are on all the compositions are also on the line. So an example would be very much if I were to take the system calcium, silicon, oxygen, ternary system, and here's the point, this is the point CaO, and over here is the point SiO2, and this is an isopleth. So I draw, same thing, an isopleth along that line. What I'm going to get is, I'm going to get the phase diagram in figure, whatever it was, 20 or something. Okay. I showed you the calcium silica phase diagram. Where the devil is it? Figure 20 or something like that. You want to look at it? Let's look at it. Up around here, right? Okay, that's it. This is an isopleth along this line. Temperature versus composition, the calcium-silica ratio. It's exactly the same thing as figure 3A, except now all the phases, all the tie lines are in that line. You have an overall composition here, you have 2 phases in equilibrium, they don't go this way, they all go this way. The tie lines are all in here because clearly, I mean, every phase on here is a mixture of CaO and SiO2. You don't have excess oxygen or less. Okay, going above the line would mean you'd have excess oxygen. You'd have to change the oxidation state of calcium and silica. You'd have excess calcium. So your tie lines all go in the plane. So in that case, this is an isopleth, but all tie lines also lie, all compositions of all phases lie along that line. So this is called a quasi-binary system. So now it looks like a binary phase diagram. Okay, so that's a ternary system. It's a quasi-binary section of a ternary system. Quasi-binary because now only one composition parameter is required. Your composition along this line is all you need. One composition variable. You have one mole fraction, one independent mole fraction. Okay, so therefore it's a quasi-binary system.
So when can we say that, okay, now we are working, this isopleth is a quasi-binary system?
When it is.
Okay, it means when there is only one.
When all the phases are in that.
Like if there is sodium, potassium and chlorine, so we can get a quasi-binary system there also.
Yeah, as long as all the phases lie, at all temperatures, lie in that plane. Now, I mean, if you really are interested in the small amount of non-stoichiometry in the system, the small amount of oxygen non-stoichiometry, then you can't treat it as a. Okay, but I mean, for all practical purposes, it's a quasi-binary system. But I mean, it depends on is the system or is it not. No system is exactly quasi-binary. I mean, this system, there is a small non-stoichiometry. The fact that there's a non-stoichiometry means that you're not right on that all the time. But okay, so there's no such thing as a purely quasi-binary system. But in this system, it would be very hard put to measure any deviation from quasi-binary behavior. So the rules of construction of the phase diagram are the same as a binary diagram. They're the same as a binary diagram. It was in the same sense before that I said that this one compound here acts as a quasi one component system. If you're just dealing with exactly the composition Ca2SiO4, then you have the solid phase is there and the liquid phase is the same composition. It acts like a one component system. On the other hand, if you were at some composition here, this is not a quasi-unary system because your tie lines, your overall composition, I mean this sounds trivial, but it's the same thing. If your overall composition is 10%, your overall composition can remain 10%, but the individual phases don't have 10% composition. At this particular 2-to-1 composition, then you are just on a point in which you're a quasi-unary. And it's the same thing here. This is quasi-binary. All the tie lines happen to lie in that plane. If you took another section across here, of course, then it's not quasi-binary. Alright, so let's go back to 3. So, this section, since it is not quasi-binary, does not look like a binary phase diagram. It has different geometrical rules. I showed you the rules of a binary diagram where eutectic type, peritectic type, minimum and maximum. I mean, there's nothing in that permits you to have something like this. Now, if this is a quasi-binary section, then all these things disappear and it looks like, well, that's the other way of telling. If you look at your phase diagram and it looks like it obeys all the rules of a quasi-binary section, then it is. Okay? Otherwise, you're going to get. Okay. If you get here, if you get 3 phase regions that are all horizontal and so on, otherwise. Okay, but so this is your isopleth. So the isopleth, the labels tell you what phases are present, but it does not tell you what the compositions of those phases are. Nor can you apply the lever rule to get the amounts of the phases present. In a binary diagram, not only do you know the composition of the phases, but the lever rule tells you how much of each. Here you can apply neither, you can not find the composition of the phase, nor can you do the lever rule, and it simply tells you when a phase appears. So it will tell you that if I take this alloy here and I cool it, that at this temperature the FCC appears. At this temperature you have the tau phase. It tells you when a phase appears or disappears, but it doesn't tell you how much of it there is or anything else. Okay, so that's an isopleth. You have other kinds of isopleths, going now to figure 4. Okay. Okay, figure 4. This is a 4-component system. Okay, so this has 4 components: iron, chrome, vanadium, carbon. Tells you over here, iron, chrome, vanadium, carbon. At a constant temperature. Since I have 4 components now, I'm going to have to keep 2 things constant. So I keep, this is at both an isotherm and an isopleth. I'm keeping the temperature constant and the total amount of carbon constant. This is, again, the total amount of carbon in the system, not in any individual phase. Okay, and so now it's mainly iron. So down here, I'm adding, this is iron, more or less. This corner here, the origin here would be iron with 0.3% carbon, and then this is the amount of chrome that's being added, and this is the amount of vanadium being added. Again, this is the total amount. Okay, so this is again, you have these regions here only tell you what phases are present. These are all solid solutions. This is the BCC solid solution. This is the M7C3 solid solution. Means it's a solid solution of vanadium, chrome, and iron. Well, actually, in this case, it would be no iron, but I guess vanadium and chrome carbides. The MC phase is the monocarbide, iron, chrome, vanadium, carbon, and so on. Okay, so once again, you have 2-phase regions, 3-phase regions, 4-phase regions, and so on, with lines in between them. These tell you if you were to change the composition and along this line and so on. If you were to start with a steel up here, you'd be a BCC plus monocarbide. As you were decreasing the amount of vanadium, you would have a FCC phase would appear at that point and so on, but they don't tell you the relative amounts or anything. And this seems to have a different stoichiometry, a different geometry than the previous diagrams did. Okay, this is another isopleth. These are all single valued phase diagrams. They're all proper phase diagrams. You're plotting one variable versus another variable, keeping other variables constant. The number of variables that you have to keep constant, of course, goes up as you increase the number of components. Figure 5. This is another kind of phase diagram, which you're seeing more and more. This is a ternary system, iron, nickel, oxygen, at 1200 degrees Celsius. And what we're plotting here is the iron-nickel ratio at the bottom versus the equilibrium oxygen pressure. So you're saying what you've got is you've got an alloy of a certain iron-nickel ratio. You put that in an equilibrium oxygen pressure at 1200 and you see what you get at equilibrium.